Hi everyone, Dr. Anna here, and this is the third segment of the rock fossil and time module. So let's jump in. We stopped at the characterization of sedimentary rock, and now we're going to start with the classification of sedimentary rock. Remember, from physical geology, we classify the sedimentary rocks into two big groups: the clastic or detrital sedimentary rocks and the chemical and biochemical. What is the big difference between the two? The first one, the clastic or detrital sedimentary rocks form strictly by physical processes, and we classify them by their grain size. The chemical and biochemical sedimentary rocks formed by chemical weathering, and the end product is that the original rocks go into true solution, and then later they will precipitate, and we have no idea about the parent rocks, while the clastic, because of the law of fragments, will tell us the original rock. But the chemical, biochemical, there is just no way to know the parent rock, the original rock. And the classification in the chemical, biochemical sedimentary rocks is happening by composition. So we're going to start with the clastic or detrital sedimentary rocks. Remember, we classify by the grain size, and we're going to talk about the brachia and conglomerate. And the grain size is larger than 2 millimeter. Then we continue with the sandstone, where it's 2 millimeter, 2.063 millimeter. Then we continue with the siltstone, which is 0.063 millimeter, 2.005 millimeter. And then we're going to finish with the mudstone and the shale, where the grain size is less than 0.005 millimeter. When we classify the plastic and detrital sedimentary rocks, we always have to talk about energy and the distance from the origin or the source area. So I have this little summary figures, and I'm going to point out to environment where the different rocks formed in. We're going to start with the brachia. The brachia important characteristics that it has angular gravel-sized grains in a finer grain matrix. Like you can see here are the grains. See, they are angular, and the matrix, which is between the grain area, are very fine grained or finer grain, different grain size, definitely. So these guys will form close to the source, because the angularity means that they didn't get transported at all, because during transportation the grains are kicking and get rounded. So when it's completely angular, that just means that it didn't get transported, so they form very close to the source area, and the energy must have been pretty fast, because when you are in the high mountains everything moves pretty fast. Now I can ask the question, what makes a rock brachia? And if you think about it just a little bit, you realize that it's angular gravel-sized rock fragments in finer grain matrix. Now, does it matter what is the color of the rock, what kind of rock fragments are in it? To define the brachia itself, you do not need to know the type of rocks in there and the color. The only thing which makes a brachia is that it has angular, gravel-sized rock fragments, and the matrix is finer grained. So the next type of rock is what you will have to know is the conglomerate. The conglomerate is very similar to the brachia. The difference is that the gravel size are rounded. So that's the main difference. If you look at this figure, it is still very close to the source area, because large grain size, they are larger than sand size, so it's larger than 2 millimeter. So we still have to put it somewhere really close to the source area. But it had to be a little bit transported because of the roundness of the rock fragment. So it must have been transported a little bit by some rivers. So the energy is still very high as well. You can see two more conglomerate pictures here. After seeing all them, now you can ask the question, what makes a rock a conglomerate? What do you think? I think after the brachia we looked at, it's very simple to see that the only difference between brachia and conglomerate is that the brachia is angular, conglomerate is rounded gravel-sized pebbles, basically. So what we say that a conglomerate is uh, rounded gravel-sized rock fragments in finer grain matrix. So it's a rock which has rounded gravel-sized rock fragments in finer grain matrix. The color and the type of rock fragments will not matter, just to define that this rock is a conglomerate. Now we step down by 1 grain size, so we are in the sand. Remember the 2 millimeter to 0.063 millimeter. You will see sand size grade throughout the rock, just like on both sides. It will form slight to moderate energy environment, and it could be closer or farther from the source area. So everywhere, anywhere in this area, basically, anywhere in this area. It's high to moderate. I said only moderate, but we can say the high else as well. So high to moderate energy environment, close to or farther from the source, because it depends on the composition of the sandstone, as we will see right away. You will have to know 3 kinds. The first one is going to be the quartz sandstone. The second one is the Arkose, and the third one is the Greywacke. So let's jump into defining quartz sandstone. So when we have a quartz sandstone, the amount of quartz in the sandstone is very, very commonly exceeding 90%. So more than 90% is going to be quartz, and the quartz grains are well sorted, most of the time rounded, and that just indicates that they have had significant transport from the source area, and their color could be depending on what kind of cement material is in it, but it could be white to tan, gray, or reddish, depending on, as I said, impurities like iron content or the oxygen level of the environment and so on. We already kind of mentioned it forms in high energy environments like beach. Anytime you go to the beach in the eastern United States, you're going to have quartz sand beaches. It could also form in desert, like the Death Valley. A lot of national parks have quartz sand sediment in them. Frequently, you will see sedimentary structures. Most of the time, it's going to be crow's bedding, like you can see on this picture right here. It's beautiful crow's bedding, most likely from Zion National Park. So if you look at the source area, it could be somewhere right here in the middle, like in deserts, or it could be on the beach. Normally, it's like moderate energy, except when it's on the beach, it's rather high because of the wave action. The next type of sandstone you will have to know is the Arkose. The Arkose is very, very characteristically potassium feldspar rich or autoclase K feldspar, and at least 25% K feldspar is going to be present. Like you can see on these pictures, like here, this is K feldspar, K feldspar, K feldspar. As you can see, there is a whole lot of them. And then about 75% quartz. Of course, you can have other rock fragments as well. Like you see a couple of them right here, like these black guys. Um, the color of these rocks are typically reddish to pinkish because of the iron oxide staining. It usually forms pretty close to the source look, so we're talking about this area because the grains are angular. So that shows you that it hasn't been traveled too far away. And normally it will occur in granitic terrain as it starts eroding away. The after the brachia conglomerate is going to be the Arkose. Sometimes you can see rocks just like Arkose, but it's a bit bigger, so it's rather brachia or conglomerate. It often have poor sorting, and it has, as I just said, it has other rock fragments and sometimes clay minerals. And the last one you will have to know is the Greywacke. And the Greywacke has rock fragments and fine-grained clay or mud matrix. So this here is an under the microscope picture, and you can see the rock fragments right here, and then it's sitting in a very fine-grained matrix. And normally those are clay or mud, and the grains are angular, as I just pointed out, and the rock is poorly sorted. It has hard, dense gray to dark gray and greenish color. So this here is a dark gray greenish color right here. Now, normally Gray forms in tectonically active area, mostly like if you have an oceanic plate boundary, and there you have the islands on the side which is not subducting. And from the island, which is really, really close to the ocean, if you think about it, from that island, it goes into the water without much transportation. So that's why the grains are usually angular, and the energy is relatively high because it comes from the mountain to the deep ocean right away. So this is a summary about the sandstone. The sandstone is very, very important, especially in historical geology, because it gives us information about the geology of the source area, remember the Arcos, it's coming from granite. If you see Greybucket, that it was tectonically active area, it tells you about the amount of transport. Remember, the quartz sandstone is far, far away from the source because everything is weathered away except for the quartz. Like Greybucket is very close to the source area. It also gives you information about the transportation material. When we talk about that, it glacier of water, like river, or it really tells us what transported it. And it also tells us the distance from the source area. Normally, the sandstone, as we talked about, will form in high to moderate energy environment, and it could be close or farther from the source area, depending on the maturity, means the composition of the rock. The next rock you will have to know is the siltstone. The siltstone is mostly containing quartz, very low amount of clay, and trace amount of feldspar, mica. Sometimes when you look at the surface of the siltstone, you can see some shiny mica particles. The grains in the siltstone are very well sorted, and they are all silt sized, which means 0.063 millimeter to 0.005 millimeter. So when you touch it with your hand, remember this, we learned it in physical geology. The siltstone is when you touch the rock and it goes in between the lines on your finger. That tells you the silt size. If it's sand size, you can feel the grain when you touch it. But the silt size is when you touch it, it colors your hand. It can have different colors, I just told you, mostly depending on the oxygen content of the environment. If there is a lot of oxygen, it's going to be light colored. If there is no oxygen, it's going to be really dark, like dark gray, dark blue, even black sometimes. So if you look at this figure right here, the siltstone is going to form anywhere in this area. If you think of the meandering rivers from physical geology, this is the area, and the floodplains of those will contain a lot of siltstone. And in the deeper water in the ocean, will have siltstone as well. If we look at the energy right here, the siltstone is going to be right around here. So it's pretty low energy environment. The next type of rock we have to talk about is going to be the mudstone and shale. These two are composed of clay with very minor amount of silt. When you think of the mudstone, and I already drew it right here, the mudstone is going to be massive, stocky, and it will not have little layers in it. When you touch it, it feels greasy, and the grains are not really going into your the lines on your finger because it's like too small. And feeling really greasy is the best way to tell by touching that rock. How do we tell the mudstone and shale apart from each other? One of the way to do that is that mudstone usually is massive, stocky, and it has no teeny tiny layers. Whereas in the shale, as you can see, it has very, very thin layers. This is what we call fissility, or the shale is fissile. Okay, so that's just the ability of the clay to split into thin layers. And it's very, very characteristic. The color of the mudstone and shale is depend on the oxygen level of the sedimentary environment. We're talking about the area where the mudstone will form right at the sink. So it's either in the deep ocean or right at the coastal swamp area. If you look at the energy level, it's really down here where the energy is extremely slow. It strictly deposits below the wave base. So it has to be, but absolutely no water movement happens. And as I said, it's in the deep water below the wave base or the coastal swamp areas. That's where it's really the water never moves. You can imagine if you've heard or have been in the Everglades area, that's a typical low energy environment where the shale is forming, and it's always black because there is no oxygen in those environments, and this is where the coal is forming. And later on, as it gets buried, and we talk about this later during the historical geology class, uh, when it gets buried, this is what will make the black shale, which is the perfect place for the fracking. And we're going to talk about fracking as well. So I guess I'm going to finish this segment right here. And in the next segment, we're going to talk about the chemical, biochemical sedimentary rocks.